In this demo, we'll explore some advanced commands and other features. So here we'll look at how the with recursive works, window partitions, row number, rank, dense rank, first value, last value, lag, and lead, how the unbounded preceding works, stored procedures, creating and executing them, creating views, creating functions, and creating triggers. And we'll also be creating tables and updating tables and all that as well. In this demo, we'll learn how to use some more advanced SQL. So this time we're going to be using Postgres. So what's Postgres? Postgres is a general purpose and object relational database management system, and it's one of the most advanced open source database systems. It was built at Berkeley in California a long time ago, and it was designed to run on Unix-like platforms, but it's also very lightweight and it runs mostly off a command line. So it doesn't come with any tools at all, except for a very thin server side. And you can do a lot of these user-defined types, table inheritance, sophisticated locking mechanism, views, rules of query, and a lot of things that you can't do in MySQL, because you can also run some code and it's also procedural. So here I have Postgres installed on Google Cloud Platform as a managed instance, and I'm using a client here from my computer, connecting by local-host via a service account to the Google Cloud Platform's Postgres instance. So let's start with the with. As we discussed in the lecture, with is the common table expression, and this specifies a temporary table result set known as the common table expression, and this is derived from a simple query. Okay, so first let's create an example table. So we have a table here, create table parts list with 3 columns. We have a whole, part, which are text columns, and then count, which is an int column, integer column. And then we are inserting some demo data here. Car engine 1, car wheel 4, engine cylinder head 1, cylinder head screw 14, wheel screw 5, car doors 4, car steering wheel 1, doors window 1. And so these are the parts for different parts of the car. Now what we can do is, okay, so let's run this. So this creates a table and inserts the 8 rows. So now we can return the number of screws that are needed to assemble the car. So in order to do that, we can create a recursive with. So it's going to look like this. So it's a with recursive list and a whole part num as, and then the select statement. Then we're going to have a union of 2 select statements here. Whole part count as num from the parts list, where the whole equals car, and then we're going to do the whole part and then count from the list from here. So we're recursively going to be calling this multiple times, and then finally we'll get and then we will keep adding the sum here and keep a running total. So let's find out the total number of screws that are required to build this car. So here we can do that with a recursive with statement. So we have with recursive, and then we're creating a list here with whole, part, and then the num. Then we have our 2 selects here, which we are doing a union, and then we have the final result here that's keeping a running total. So this part is going to recursively be done, while this part is going to keep adding where this part is going to provide us with the final answer. So we get a sum of 34. So let's take a look at and see if this actually is correct. So here we can see that the wheel screw 5, this means that each wheel requires 5 screws, and we can also see that there are 4 wheels in the car. So that's 4 times 520, and we can see that the cylinder head requires 14 screws, and there is only 1 cylinder head in the engine, and there is 1 engine in the car. So that's just 14 plus 20, so that's 34, which was the result that we previously got. So it recursively traversed through this table and then got the answer that we were looking for. So that's the example of using a recursive. Okay, so now let's look at the window functions. So this is a fairly popular example, so you might have seen it before. So we're going to create two tables here, one for products and one for product groups. So we're creating a table called product groups, and we're going to do a serial primary key and a group name, and another table called for products, where we have the product ID, product name, price, group ID, and we're going to use this as a foreign key to reference to our product groups table. So we run that. So we created those two. Now let's add some data into those. Right, so we're doing an insert into product groups. We're adding smartphone, tablet, and laptop. These are the product groups, and then we're adding these products, which are Microsoft Lumia, HTC One, Lenovo ThinkPad, and so on. So these are different products. These are different computers and smartphones and the tablets mixture, and then we are categorizing them here with the product groups. So let's refresh our tables. See the data in product groups, and then see the data in products. Okay, that looks fine. So if we have product ID, product name, price, and then the group ID, and the group ID corresponds to the category of whether it's a smartphone, laptop, or a tablet. So now we can start with just the aggregate function. So if we just do a select average price from products, so that just gives you the average price of 586.36 and so on. So now we can do a little bit of grouping to make it a little more meaningful, because so if you're mixing the average price of tablets and laptops and smartphones, that's not really very useful. So here we are doing select group name average price from products, and then we are doing an inner join to product groups using group ID and then group by group name. So this should give us the average per group. So this gives us the average price for a smartphone, an average price for a laptop, a tablet, and then an average price for a laptop. So by using a partition, we can actually see the actual product name as well. So in this case, this is pretty bland, so we can tell by the category. But if we also want to look at the product name and then see what category it belongs to, and then the average price, then you can still do that by using a self join, but you can't go further than that. So here what we're doing is we're selecting the product name, price, group name, and the average price over the partition by group name. And then we're doing a from products inner join product groups using group ID. So here we're simply doing a partition for the group. So this gives us the result where we have the product names, the price, the group names, and still the average price, but the average is per group. So now let's look at the row number. So here we have pretty much the same query as before, but we added row number here. So this basically, the row number function, it just assigns a sequential number to each row in each partition. So if we run this, so we have a row number here, and that tells you 1, 2, 3, 4, and then 1, 2, 3, 4, and then 1, 2, 3. So this is per partition, so it's counting. Now we can also use rank. Instead of row number, we replace that with rank, and now we can see the rank for each within each category. So the rank function assigns ranking within an ordered partition, and if the rows have the same values, then the rank function assigns the same rank with the next ranking skipped. So that's why you have 1, 1, and then 3 and 4, because you can see that these two, the price is the same. So it's ranking them as both of them are tied as 1. And here for the smartphones, they're all different prices. So you get 1, 2, 3, 4. And likewise for the tablets, they're also all different prices. So you can actually rank them. Now, if you don't like the fact that it's skipping the number, then you can use something called a dense rank. So instead of rank, you can say dense underscore rank, and this function will provide you without the skipping. So in this case, we can see 1, 1. They're both still tied, but the next number is actually 2 and then 3 instead of skipping to 3 and 4. So now let's look at the first value and last value. So here we have the first value for price, and the first value function returns a value that's evaluated against the first row within its partition. So it's basically finding out what's the lowest price per each group. So in our group of laptops, 700 is the lowest price, and then in our group of smartphones, 200 is the lowest price, and then in our group of tablets, 150 is the lowest price. In a similar fashion, we can use last value, and that's going to give us the last value per each partition. So in this case, it's giving us the highest price per group, and that's 1200, 900, and then 700. Now let's look at lag and lead. So the lag function has the ability to access data from the previous row, and then the lead function can access data from the next row. So here we have product name, group, price, and then lag, and then price and 1, partition by group, order by price, and then we also have as previous price, and then lag, and then the price 1. So in this column, what's happening is we're looking for the previous price. So for the first one, it's null because the previous price of this is nothing. The second one, it's 700 because this is the current and then this is the previous, and the difference between the current and the previous is 0. And then here we have 700 is the previous again, but then the current minus the previous is 100. And likewise you have 800 here. That's because the previous one is 800, and then we are subtracting 1200 and 800 here, which is current minus previous, and then we get 400. And this one is again null because we're starting again for each partition. Now let's look at lead. So in this case, we have 700. This is the current price, and this is the next price. So if you subtract both of them, it's 0. And in this case, this is the current price, and the next price is 800. So we put the 800 here, and if you subtract that, you get minus 100. In this row, the current price is 800, and the next price is 1200. So subtract and you get minus 400, and so on. So Postgres allows stored procedures, functions, indexes, triggers, and views. Stored procedures define functions for creating triggers or custom aggregate functions, and stored procedures also add many procedural features like control structures and complex calculations. So stored procedures are like black boxes, so you can write some code that you want even in other languages, and then you can just have that stored procedure called whenever you need to run or process. So the advantages of stored procedures is that the stored procedure is already compiled. It's going to be much faster, and it's a lot better in terms of performance. It's also reusable in many applications. So once you develop a stored procedure, you can use that in different places and different queries and so on. It also reduces the number of round trips between the applications and the database servers. That's because all the SQL statements are wrapped inside a function stored in the Postgres database server. But there are some disadvantages as well, because you have to actually develop these stored procedures, and that requires special skills. So you need to hire software developers to do that. And they're also difficult to manage because in terms of if there are new updates or changes and different versions, then you'll have to go and rewrite the code and manage and maintain those. And they're also not portable because the Microsoft SQL Server stored procedure might have a different syntax compared to Oracle or Postgres. Right, so when you're creating functions or stored procedures, you need to know how to declare variables, and you need to know how to initialize these variables as well. So let's look at an example here. So here we declared 4 different variables. The first one is counter, which is an integer 1. The first name string, last name is also a string with John and Doe, and then the payment is a numeric, is a decimal with 20.5, and then we can say raise notice, and then we can use the percentages as wildcards and pass in the variables that we just declared. So this is a very simple and basic way of being able to declare variables. Now the reason we did the begin is in order to declare the block. So it will have to do these things in the right order. So for example, we can see what the order looks like. So here in this example, what we're doing is we first declared the created at, and then we're just passing the current time, the current timestamp, and then we're doing in this block raise notice and created at, and then we're waiting for 10 seconds and then print out the variable again. So it's the same variable we're printing, but we're putting a 10-second delay in between. But when you execute this, we can see that the whole block is executing at the same time. It's not doing this and then waiting 10 seconds and then printing this out. Both of them are printed at the same time. So that shows that this whole block is being executed at the same time. Okay, so let's look at an example of creating a stored procedure. So before doing that, let's add some dummy data and a table here. We're creating a table called accounts. So there are 3 columns here. There is ID, there is name, and then there is balance. And then we are inserting 2 rows here. One Bob 10,000 and Alice 10,000. So Bob and Alice have 10,000 credits. You can see the 2 rows here. So now let's create a stored procedure. So here we're creating a stored procedure called transfer, and we're doing a create or replace procedure. So in case the same one exists, then we're just going to overwrite that. And it's going to take some inputs, 2 integers and a decimal. We have the begin and end statement here. So there are 2 parts to this. One is it's updating the accounts table and setting the balance to subtract the balance from the first person, and then the second part is updating the accounts table to add the balance to the second person. So it's taking int, and then the decimal. So what it's doing is it's getting the ID of one person, the ID of a second person, and then the amount. So what the stored procedure does is it's so this is transferring balance between these 2 people. So we can transfer 100 credits or 1,000 credits, and that will debit and credit the right people automatically. So let's create this. So the procedure is created. So now we can call this procedure. And doing that is simply doing a call and then transfer and then the correct inputs, in this case 1 and 2 and 1,000. So we're transferring from person 1 to person 2 with person ID 1, ID 2, and then the amount is 1,000. So run this. And now the procedure is complete, so we don't get any results here. So we have to check the table, and we can see that the table has been updated with Bob has less money and Alice has more money. So here we're creating a view. A view is similar to a table, but it's a virtual table. So the data is not really existing underneath the view, but it's based on real tables, and the view has different pros and cons because you're able to use them in different reports while you're not really changing the underlying data structure. in case the tables actually change or the table data actually changes, then the views will reflect automatically unless the table structure changes, then you'll have to recreate the view. Every time a view is actually called, the data is recalculated every time. So the view is not necessarily very more efficient or better than table. At the same time, you can also create views with fewer columns and better techniques in order to improve the performance as well. So in this case, we're creating a view called Bob underscore B, and we're doing a select name ID from accounts where ID equals 1. So in this case, we are only going to be showing Bob's balance here. So we run this. So we created this view. So from now we can start using this as a table. So now we can do and that will just give us one row here. So we can assign this to only Bob, and Bob can only see his balance in this case. Now, in a similar way, we can also, so we can create another view here, for example, called create view balances, and then we're selecting the ID and the balance from accounts. So in this case, what happens is select star from balances. So what we're doing here is if we do a select star from balances, we can only see the ID and the amounts here. So in this case, we are obscuring the names of the people. So we can give this view access to certain people and not actually give them access to the underlying table and all the different columns. So in this case, it could be a security measure. But of course, if you actually want to obfuscate the data, then you'll actually have to anonymize the IDs as well, because these IDs can be referenced back to those actual people. Now we can also create an index on a certain column. So by default, the primary key will automatically be indexed. So in this case, in our accounts table, if we think that there's going to be a lot of lookups based on the name, so then we can create an index based on that name. So it's create then the index name and then on the table name and then the column name. So this creates an index on the name column in the accounts table. So if this is going to be a large table and there's going to be a lot of queries and lookups based on the name, then it will make sense to create the index here. So now when you run queries on this table, then it's going to, the query plan is going to show that it's using the name field as well, the name column, to calculate the cost and to also create that query. However, the problem is that if you create too many indexes, or if the table is really large, every time you add or update or make changes to that table, then that index needs to be updated as well. So the database is going to reindex itself, or you can rebuild indexes manually, and these are all database level techniques. Okay, so there are three parts to this. So we're creating a table, a function, and a trigger. The purpose of creating all of this is to create some audit trail. So we created previously this accounts table where you have Bob and Alice and their balance. Now, if there are any changes in that balance, then we want to trigger a function which will write to an audit table. So here we're creating an audit table, customer audits, and this has the name, balance, and then the timestamp of when the change actually occurred. The function, what it's doing is it's called log balance changes, and it's doing if new balance is not equal to old balance, then insert into this table the name, balance, and changed on, and we want to store the old name, the old balance, and the current timestamp. And the way the trigger works is create trigger, the name of the trigger, And when do you want the trigger to happen? Before the update. Where? On accounts table. How? On each row. And what should happen? We should execute this procedure. So whenever there's an update, or this function should be executed on the accounts table for each row. Okay, so we need to provide the language and the cost as well, or you'll get an error. So now the table has been created. So now let's execute this part and then apply the trigger. And the trigger has been applied. So now let's test this out by actually running our stored procedure as before. So now let's run the stored procedure again. And now let's check our tables. And we can see that there are new rows that are created here, and we can see the old values of these balances and our current timestamp for these. So if we run this again and run this again, so now we can see that now it added 2 more rows. So now it's keeping an audit trail of what these changes are being made. So whenever there's a change in the accounts table, that change is going to be written to this, but only for updates in this case. So we can create other triggers for when there is an insert or when there is a delete, and for other actions as well. Okay, so now let's look at how the unbounded preceding works. So this is the example that we saw in the lecture as well. With data TA as the values 1, 1, 2, 5, 3, 3, 4, 5, 5, 4, 6, 11, then we're doing a select TA average of A over order by T rows between 1 preceding and 1 following from data. And then we want to group by the T. So what we're doing here is what we're doing here is to calculate the average amount in a frame of 3 days. So we are looking for 1 preceding and 1 following. So from the current row, we want 1 above and 1 below. So in this case, we have 1 and 1. So the average is just 3 for the first row. For the second row, you have 2 and 5. So you have for the first row, you have 1 plus 5, and then you divide by 2, so you get 3. So the second row, you have, for the 2, 5, you have 1 above and 1 below. So you have 1 plus 5 plus 3, and then you divide by 3, so you get 3 again. In this case, it's 5 plus 3 plus 5, and then you divide by 3. Now we'll do a second query here with data TA as, again, the same values. Now this time we are doing rows between unbounded preceding and the current row. So if we run that, then we get this. So now we're getting a sum that's 1, 6, 9, 14, 18, and 29. So in this case, the frame's lower bound is infinite. And now we are basically calculating the running total in this case. So it's 1, and then 1 plus 5 is 6, and then 1 plus 5 plus 3 is 9, 1 plus 5 plus 3 plus 5 is 14, and so on.